Okay, today let's do some system design on web crawler. So let's first talk about the functional requirements. So basically, we want to crawl all the web content, static content, basically from HTML, from roughly 1 million websites, 1 billion websites, sorry. For 1 billion websites. And we will basically parse the content, store the content, and utilize it via search index. We're gonna build a search index on top of the content, or we're gonna leveraging some a large language model grounding use cases using it. So we're gonna store content for other use cases, like last search, LLM grounding. And the third one is that we want to be able to crawl everything within 1 week. Crawl within 1 week. Okay, so let's focusing on these three as of now. So non-functional requirements. First of all, we want to be polite. Means we want to follow the rules that give via each domain by the robot.txt file they provide. Robot.txt. Second of all, we wanted to we don't want to miss any website crawling. No missing. Yeah. And okay, so and we already talked about that we want to crawl the scaling of 1 billion websites within 1 week. In 1 week. Okay. So let's do some capacity estimation really quickly. So capacity estimation. Okay, let's say we have 1 billion websites, and each website contains 1 million of it. The HTML file is in average 1 million per website. And like in this case, we will be needing, so this is the one-liner. So we will need a petabyte data storage. In this case. So also, since we want to crawl 1 billion websites within 1 week, so 1 week is roughly 600K seconds. So in this case, our QPS would be roughly 1 billion over 600K, which is roughly per second. That. Okay. So 1 thing. Yeah, this sounds good. So this is a lot, and we want to be able to use some single machine to do this. So, and we need to be scaling well to handle all those traffic. So even though we have multiple different threads, we should also be utilize multiple machines uh, to do this. Okay. Next thing we will talk about workflow. So how does the crawler work in data flow perspective? Okay, first of all, we have a seed URLs into frontier view. Okay, we have a set of seed URLs and we put them into the frontier queue. And then consume URLs from queue. Get IP address via DNS, domain name service. Okay. Make HTTP request from the IP address. Download HTML file. Parse file, store file, store content. And then fetch URLs from HTML, feed into frontier queue. Repeat. One, two, five. Okay. So also, these are our workflows of how the web crawler is working. However, we need some functionality of deduping. So for example, whenever we are consuming the URLs from Q, we need to do the deduplication. We need deduplication whenever we're checking the URL. If it's a duplicated, then we won't go to DNS to get the IP. Another thing is that, so when we have the file, and when we're parsing the file, storing the file, fetch URLs from file, we need that deduplication as well, so that we won't repeatedly parsing and storing and processing the same URLs again and again. Okay, so these are the rough like workflow, and let's start the web crawler high level design. Okay, so first thing, this is our frontier view we talked about. And so we are gonna need a crawler service. Okay, what it does is that DNS, it talk to DNS, it do HTTP request. Okay, and okay, potentially it's gonna do URL dedupe. And send it to so store content. Send it to person. Okay. So in this case, this service is actually talking to DNS, get IP from DNS, and possibly website. So let's mimic this website. It's basically having an HTTP call from that website and like download the HTML from it. Actually, it needs to dedupe URL first. So our storage, because it has to store somewhere about the HTML file, the content file. So we could basically use a blob storage because it's cheaper compared with file HDFS. etc. kinds of file systems. And let's say HTML store. And we also need a database that contains the metadata of the website. Metadata DB. So our data could be like this. So URL and potentially URL hash value and S3 URL and content wise. Okay, so HTML wise, S3 URL robot txt wise. Since, okay, so we use S3 as the source of truth or storage for the HTML content and the robot txt. So we basically need a URL placeholder from metadata database to show us where can we download those HTML and where can we download the robot txt. Okay. So it basically write to S3, write to upload the HTML to S3 and record that metadata. The time step. And so we could utilize that last rolled timestamp. Because within the txt is robot txt, it tells us, do we have permission to crawl this URL, and how often can we basically crawl this URL, and that's why we need to store the last crawled timestamp so that we won't violate the robot txt policy. So once there has been recorded and it needs to be sent to the parser service. So after parsing, it also needs to be write back to S3 because S3 could contain parsed content. So this is something different from the raw URL storage. The parsed content could be either like all in different format, and get ready for for example, the Elasticsearch indexing or the large language model knowledge base. So it could be something really different from the raw HTML. So yeah, so once it's get parsed, another thing it will does is that, okay, it also needed to dedupe the content, not the URL dedupe, but the content dedupe. Okay. Second of all is that upload parsed content to S3. Fetch URLs from HTML. Send to frontier queue. These are the functions for the parser host, parser service, basically. In order to trigger the crawler, we need a set of seed URLs in the beginning. So, okay. So this is a rough diagram of a web crawler. So let's go back to our requirements, double check. So first of all, we want to crawl the website and store the content and crawl it within 1 week. So we want to be polite, and because we follow the robot.txt policies, and we don't want our crawl to be missing. And like we have to be crawling 1 billion website within 1 week. So okay, let's talk about how do we want to scale the system, and how do we want to be like fault tolerant in the sense. So first of all, so we could, so first of all, let's think about the frontier queue. So we could basically either use in-memory queue like SQS, or we could utilize Spark for the frontier queue and Flink for the crawl service. SQS or Kafka plus Flink. So the data over here should be URL and last crawl, last timestamp. So basically, like telling us what's the last timestamp that we crawled the same domain. So like if we don't care about the ordering, which is our cases over here, we could definitely use in-memory queue for our act as our frontier queue. So, and I mean, even Kafka also works, and Kafka could be partitioning the same way as the cross service. So I don't think there's an obvious trade-off over here. So let's just keep it simple as SQS, AWS managed. So, and if we have some bad URLs that we couldn't process it, then we could have a that letter queue, and we could basically post processing and do analysis for the bad URLs over here. And we store them all the information into the dead letter queue. And if for example, if one of the processing is failing, we definitely want to reprocess the URL. So in this case, we need something that is exponential backoff. So since we URL, so exponential backoff. Okay, so AWS SQS is already having that mechanism managing for us. So we could utilize the function of SQS to apply our exponential backoff and the maximum retry of like 3 times or so. So, and use that letter queue for all those URLs that cannot be requested from DNS or cannot be fetched from the website via HTTP call, or any kinds of failure. We could basically, after the maximum retry, we could basically send it to that letter queue. So yeah, and SQS is infinitely managed and infinitely scalable because it's AWS managed. So crawler service, we could use a container or like any service that can do the same job. So it's actually needs to deduplicate first of all. So for the deduplication, we basically need to store, so let's say we have 1 billion of a website, and if for the hash value of the URL, it might be byte, 8 bytes. So overall, it's just 8 gigabytes. So we can feed this into memory. Okay, in this case, we could basically keep a set of cache within the server. Instead of going back to database and see if this URL has been processed or not. URL. Okay, so that we make the deduplication really fast. So, okay, that's it. Another thing we can do is that we could utilize another queue to decoupling the crawler and the parser. So SQS. So this is for decoupling both the crawler service and parser service and reduce the like workload if like a so for example one service is actually uh, having a lot of content while other services are having low content. So, and we don't want to make the service very so highly overloaded. So SQS could reduce the spike for us. And for the deduping the content, so we can also store the URL, we already have URL hash, and we can also have the content hash. And same thing that we can do the hash content hash. Okay, so since we already know the URL cache can store in memory because the hash value of URL could be 8 bytes or so, the content can do the same thing. Even though it's a double, we use a double digits to store the hash value of the content. It's just like 16 gigabytes or so, and it's totally manageable via the cache of the current virtual machines of the service. So it's not like a big issue. So however, once there's a problem when we're having multiple different servers, like multiple different crawler servers or parser service, and if the problem over here is that we wanted to keep the hash value for each of the server in sync. For example, we have other service 2 that and it also contain content cache 2. Okay, so what we can do here is that we could use a anti-entropy mechanism in offline process. Or yeah, so it's not in critical path, not impact critical. To keep hash in sync. So something like a CRDT or Merkle tree could help us to do this. And we could basically managing them via Zookeeper and help us to like manage all the different services and heartbeat of the service, and if any failures is happening via the service, so we could basically use Zookeeper to help us coordinate and managing the service. Okay, same as the crawler service over here. Okay, so over here we also have a exponential retry. For the database, it's actually the structure of the database is fairly simple and structured. So we could simply use a MySQL database to store everything listed over here, because we are not gonna store anything else like actually. So we could use a single leader replication and have like multiple replicas and accept write from a leader, single leader. And we could also, okay, so let's say, for example, we have one billing rows that is roughly a gigabytes like in scale. So I think for the metadata database, so we don't need a lot of partitioning, because if we just want to store 1 billion rows, it will roughly one cluster or two could definitely solve our problem. And I mean, two like two replicas each one, and at I mean maybe one leader could resolve this problem with two replicas. We don't even need any partitioning, because we're just saving 1 billion rows. So right, and if we want to load robot txt, so okay, when we're applying the robot txt over here, so it's basically downloaded from the website itself and store it to S3. So, and we apply a timestamp to our URL and parsing it and send it back to the frontier. And if the last timestamp is not actually, so we can add a next timestamp. Yeah. So in this case, because our crawler and parser already know the robot txt policy, so we can add a message to the queue saying that this is the last timestamp, this is the next timestamp. So, or even in this case, only the next timestamp will be enough. So, and tell us if this can be commit. Okay, let's say the crawler service consume a message from the queue. However, it's not yet coming to the next timestamp. It won't commit to consume to the queue, and it will be persistent into the queue still, and the next time whenever like the next timestamp is ready, so the crawler could commit to the queue saying that it's being consumed by me. So and the frontier queue could could remove that kind of message. Yeah. Going back to all the requirements, I think we have already covered everything over here, and thank you for listening.